Okay, I think you're ready to start. Welcome everyone for this third day of press conferences. And this press conference is on space weather impacts and forecasting. And we have three speakers. Norma Crosby is our EGU division president of Solar Terrestrial Sciences, and she's also a research scientist at the Belgium Institute for Space Aeronomy in Brussels. Andrzej Krakowski, if I'm doing that well, is an associate professor at the University of Warmia and Mazuri in Poland, and Manuel Grande is a professor at this one is hard for me as well. Aberystwyth University in Wales. And we can start, Norma. Thank you.
Okay, thank you very much, Barbara. Yeah, thank you. Yeah, and welcome, and thank you for coming to this press conference that we have looked forward to. So we'll be talking about space weather. I just briefly start with one slide introducing the topic, and then the other speakers, including myself, will go more into detail, like what we do concerning space weather and also the phenomenon causing the space weather. So basically, space weather concerns how the solar activity influences the space environment in, for example, near-Earth space, where we have satellites, but also sometimes you can find effects all the way on the ground. Now, any solar system with a star will, of course, have its own local space weather. And it's our sun, our local star, that drives our space weather. Now, these beautiful images on the left, they're actually from Skylab, which was one of the first spacecraft it was a station, but on board there were detectors that actually gave these beautiful images of the sun. And one became more aware of the fact that the sun does create, for example, different types of phenomenon that can have effects. And actually Skylab itself perished because of the activity of the sun, of an effect called drag, that is basically the heating of the atmosphere. So there people became really aware of space weather. But again, it was not the term space weather wasn't used, that's more a recent term. Now, as I said, space weather covers basically everything here in our solar system. And we're going to hear about talks about the local space weather at Earth, so where we have the satellites, for example, in geostationary orbit. We'll also hear about the ionospheric effects from our speaker, and also about space weather on other planets. So I think it will give you really a nice overview. One point, space weather, it's an application-oriented discipline and addresses the need of users. So it's actually, for example, the satellite operators, the astronauts that are out there in space studying, because of course space weather not only can influence technical aspects, but also biological effects. So with this, I'm going to introduce you to a project. It's actually under the Framework Program 7 of the European Commission called COMSEP. The acronym means Coronal Mass Ejections and Solar Energetic Particles, Forecasting the Space Weather Impact. It's a consortium of 7 teams here in Europe, and it's ourselves, the Belgium Institute for Space Energy, we are the coordinator of the project. We also have 3 external collaborators, 2 from the United States and 1 from India. And this is our project website, as you see. So what are the main impacts of this EU project? Why do we actually have it? It complements the European Space Agency's space situational awareness activities for security of space assets from space weather events. So the acronym SSA for Space Situational Awareness, basically it covers space weather, near-Earth objects, but also surveillance and tracking of different objects in space. With COMSEP, we are providing a new service for vulnerable technologies in space. So this can be the satellites, as I mentioned, the astronauts, but also on the ground. For example, you can have corrosion effects in pipelines, and also effects felt on power grid systems for very extreme events. I'll go a little more into detail on my next slide. And then what's important, this project is a cross-collaboration between 2 communities that usually don't work so much together. So it's the solar energetic particle community and the coronal mass ejection community, as well as the terrestrial effect scientific communities. So having teams with different know-how, we like complementing each other, and thus we'll be able to provide a better product for the user community. And basically what we are doing, we are creating an alert system for different phenomena, which I will get back to. And finally, the impact too is to increase both international and European collaboration on these efforts of space weather research and forecast. Now what I've done here is just a schematic overview of actually how space weather has evolved so much in the 50 years. So back in '62, there was actually a special issue of a bulletin of the Atomic Scientist concerning solar-terrestrial relations. And one article written by Goldberg talked about solar activity. And this is actually the first space weather cartoon I found on the internet and journals. And what's really cute about it, already then they have an impression that there's actually something going on the sun that's influencing our Earth. And here their idea was it's some type of particles, but again, in those days they did not know there was something called coronal mass ejections. And this phenomenon from the sun was only discovered when we actually were able to build coronagraphs, which is a detector that covers the bright part of the sun, and then you can see the lighter corona, which is all around the sun. And in the corona, I'll show you an image of that, how that you see these effects. So if we go to number 2 here, what we see, especially during the space era, but already before, people were actually measuring sunspot number also with ground-based observations. So those are those black spots you see on the sun with different types of detectors. And we know that there's an 11-year cycle of the solar cycle. So at times there are not very many sunspots, and at times there are more sunspots. So this would be like the maximum part of the solar cycle. Currently, we indeed are in the maximum of the current solar cycle. At the maximum, and also especially at the declining phase, you have a phenomenon called coronal mass ejection. So what we see here in the movie, this is this coronagraph I was talking about. So it's blocking the bright part of the sun. So we go back. So you see this blob of matter full of plasma particles, magnetic fields, get thrown out from the space. Now these, what we see here, are thrown out on the sides of the sun. But in cases where they are thrown towards Earth, that's when we start to worry, because in that effect, they will come, they will interact with the Earth's magnetosphere, which is our magnetic field around the Earth, and that will cause something called magnetic storms, geomagnetic storms. And that's one issue we are working with in this concept project. The other one is actually all the white spots you see on these images. When you have these coronal mass ejections, there will be a shock produced, and that will accelerate energetic particles. And those energetic particles are also worrisome. So it's these two phenomena, geomagnetic storms induced by coronal mass ejections and solar energetic particles. And finally, what I'm showing here in image 3 is that our project actually covers a huge span of user communities. So finally, this is just an image. I won't go into detail, but the project has both science work packages covering these different phenomena. It also has a work package optimizing the models that we are developing and also the data we are using. And then finally, in the middle, you will see this alert system we are creating, and will be based on the way we define risk for the system. So with that, I say thank you, and yeah, we go to the next. So it's number 3. Yeah?
Okay. Norma has talked to you about the user applications of space weather at Earth. What I wanted to emphasize to you was the multidisciplinary nature of this study, and the fact that, of course, because the whole solar system is a coupled system, these effects are just as important, in some ways more important, at other planets. Norma is the solar terrestrial president of EGU. I used to be the planetary president of EGU. So these things really span discipline boundaries. So first of all, I was just showing you, this was a recent press release from a couple of colleagues at Aberystwyth, and this is a solar tornado identified in the atmosphere of the sun in a NASA movie. So this was a nice first. But why I wanted to show that to you was just to emphasize that when we look at the sun, we think of the sun as being a nice, round, stable thing that always looks the same. If you look at other wavelengths, if you look at it in other ways, the sun is very dynamic. You have storms and things going on all the time. So just because what we see with our eyes is stable, it doesn't mean that the actual environment of the sun is stable at all. It's intensely active, and that activity affects not only our own planet but the other planets in the solar system. I wanted to just mention a new technique which, again, we've been using at Aberystwyth, which is interplanetary scintillation. I haven't got time to explain how that works in great detail, but what happens with this is, Norma showed you the pictures of coronal mass ejections leaving the sun. These blobs are schematic coronal mass ejections. And what we do is, using radio telescopes on the ground, we look at distant stars, pulsars in fact, and so these coronal mass ejections go between us and the distant stars. And when they do that, then we can map where the coronal mass ejections are. And this is a very new and very powerful technique, and enables us, if this is going to work, oh dear, it was working earlier, that one isn't working either. Oh, this is very annoying. Let's try one more time. No, what we should be. This is a reconstruction of the coronal mass ejection, and what we should be seeing here is this is the sun in the middle. This is the Earth, and we should be seeing this large blobby structure that emerges out over the Earth and over the other planets. So now we're able to reconstruct and do to see this space weather coming towards us and other planets. This again should be an example of a more stable configuration, and again it's chosen not to work. That's very annoying. Just to prove to you that this that these reconstructions are true, and I won't show you this movie because you've already seen enough failed movies. This is a movie of the coronal mass ejection, and this is the planet Venus here. And we were lucky enough in 2009 to have a spacecraft orbiting Venus at the moment that we could see a coronal mass ejection with this IPS technique flowing over Venus. And so we were able to look at the actual data from the spacecraft that was orbiting Venus and see that, yes, absolutely, this coronal mass ejection was really hitting Venus when we thought it was. So it was very nice to know that what we were predicting does in fact work. You couldn't do that at this planet, but you can make that that test at another planet. Now again, this is not going to work, I bet you. Oh dear. This is a lovely little video, which was working earlier. Maybe I'll try and get it set up or show it to you on the laptop. This is a comet. So this is the comet and this is its tail. And what happens is that a coronal mass ejection starts from this side, hits the comet, and knocks the tail off the comet. So you would see the comet losing its tail. And that again is, if you want to come up afterwards and have a look, I can perhaps get that working. Oh, and this one has chosen to work. That's very nice of it. Okay, this is my final demonstration. As Norma said, we're in solar maximum at the minute, and so therefore people are very conscious of space weather effects, and particularly in the at the start of this year, there were a lot of very large solar flares and solar coronal mass ejections, and we certainly got rung up several times by the BBC and other organisations and saying, you know, is this going to be the big one? Is this the one that's really going to have serious Earth effects? And what was interesting about this particular one, this is a prediction from NASA. This is Earth here, and this is Mars. And what we were able to say for this particular one was, no, it's not going to do anything at all very much to Earth. But if you were sitting on Mars, you'd be in trouble. This is the Mars Planetary Service Laboratory, which was flying to Mars at that point, and at the moment that the coronal mass ejection, its space weather instruments were turned on at that moment, and as the moment that the coronal mass ejection flew over it, generate or saw an absolutely huge amount of radiation. That's all right for a robot because the robot could be designed to have to cope with large amounts of radiation. But if it had been pilots in a spacecraft, then that would have been a very, very serious event indeed. Perhaps the reason why we're not going to send people to Mars anytime in the near future. So, as Norma said, these are user-driven applications. There are certainly user-driven applications at other planets rather than just at Earth. For example, if you want to go to Mars, the other one that we're very involved with at the minute, you may have seen, is that there's a new ESA mission just being selected to go to Europa and Jupiter, and we've been doing a lot of radiation modelling for that because the space weather at Jupiter and Europa is absolutely evil. And so what the point here is just that it's not just Earth. In some ways, other planets are more vulnerable than Earth, and our interests on those planets are very much dependent on being able to understand and predict space weather.
Okay, first. In my presentation, I would like very shortly talk about real-time monitoring of the Earth ionosphere for space weather services using GNSS global navigation satellite system such as GPS, GLONASS, and also maybe in the future Galileo systems. I am currently chairman of the IGS. It is International GNSS Service Ionospheric Working Group. In order to generate the combined global IGS vertical TEC maps, total electron content maps, the several steps are needed. According to the raw GNSS data, they are provided by the very dense ground-based GNSS network, IGS GNSS network. Presently, the IGS manage station of about 384 station, but many of them covering the continental north hemisphere. It is global. Just a moment. This is global network, European permanent network, Arctic and Antarctic network. The IGS Ionosphere Working Group start to generate global vertical TEC maps in June 1998. This has been the main activity so far performed by 4 IGS Associate Analysis Centers such as CODE from University of Bern from Switzerland, ESA, NASA, and also Technische University in Barcelona in Spain. This IGS ionosphere maps is a result of combination of TEC maps derived from different analysis center by using wave computed by the validation center by, from GPS data in order to get a more accurate products. On this picture you can see the data flow required to generate IGS vertical TEC maps from IGS GNSS ground-based data by the IGS Ionosphere Analysis Centers, IGS Ionosphere Validation Center, IGS Ionosphere Combination Center to IGS ionosphere products such as final IGS vertical TC maps, rapid IGS vertical TC map, and also IGS predicted TC maps. And on this picture present an examples of final IGS global ionospheric maps for on 21st May 2010. Rapid IGS vertical TC maps, and also, for example, predicted IGS vertical TC maps for 1 and 2 days ahead, for 1 day in June and November 2010, and also for comparison, you can see IGS final global ionospheric maps. We have very good agreement between predicted and final products. And this picture present some comparison of international reference ionosphere maps with IGS final Yonex maps for minimum solar activity from 2008, and also differences between IGS Yonex and IGS final IGS Yonex and TC maps and IRI TC maps, and you can see very big differences up to 100%. Because IRI TC map, it is model, predicted model, and IRI groups ask me to update IRI maps from IGS TC maps from ground base measurements. And now I would like a little talk about occultation GNSS measurements. For example, from new Taiwan mission Formosat 3 Cosmic. It is 6 satellites with GPS receivers on board satellite, and from this measurement we can obtain tomography maps, and you can see an example for quiet and disturbed days, and you can see very big positive with enhancement of total electron content for disturbed day, and also for comparison IGS final TC maps. We also study using GPS data the TC fluctuation over North Pole. We study the fluctuation using ROT parameter and also using ROT parameters based on standard deviation of ROT. And this picture presents the dynamics of oval irregularities over North Pole for disturbed day and for quiet day with 10 minutes time resolution. There's a picture show daily with daily resolution also dynamics of oval irregularities for quiet day and also for disturbed days. And last information, for example, 2 years ago in my country, in Poland, we established very dense GNSS network, ASG EUPOS network, with about 100 GNSS, GPS plus GLONASS receivers, especially for precise RTK, real-time kinematic positioning. And from DESE network, we permanently elaborate ionosphere over station, and you can see changes of TC values for quiet, first May and third May, and disturbed day, second May of 2010, and very big positive effect you can observe about noon, yes, on second May. There's maps we create with 5-minute time resolution. Yes, thank you very much.
Thank you very much. It's a shame that some of Manuel's videos didn't work, but hopefully there's some time in the end to come here and see them. Are there any questions? No? Nothing from the web stream either?
Emily Baldwin, space science writer. Manuel, you mentioned the event that struck Mars and not Earth. What sort of protection measures would a human base have to take to sort of prevent them from being affected by such an event?
The real problem, I think, is not when you're on the surface, because then you can always, pile up rocks and all the rest of it. The real problem is when you're stuck halfway between Earth and Mars. And in that situation, there's not a lot you can do, actually. What they do is the idea is to make lead tubes that people crawl inside. If you were being gory about it, the most likely thing that happens is that you'll get a cancer which will kill you in 30 years' time. So if you only send old people to Mars, it's all right. But the chances of something like that happening on the way are quite major. I mean, we have been doing modelling of the radiation environment on Mars. It varies a lot because Mars, the vertical up and down, just the landscape. You've got Olympus Mons, which is out the top of the atmosphere essentially, whereas you've also got deep valleys. So different places, although it's a thin atmosphere, but actually it varies quite a lot. You also don't have a magnetic field on Mars, which and very little atmosphere, so you've got very little protection from the space and weather environment. But having said all that, I would have thought that a few inches of rock would be fine.
Thank you. Any more questions? Oh, it seems there's one from the web stream.
It's a question for Ms. Crosby. What are the Earth-based risks associated with space weather? You mentioned corresponding pipelines. Is there anything else? And is this all just the effect of the extra radiation?
Yeah, very good question. Actually, concerning the solar energetic particle events, when they interact with especially with the poles of the Earth, because we have this magnetic field around Earth, it shields from most of the radiation, but at the poles there are possibility of very high energetic particles to come down and interact with the ionosphere. And in that fact, you have a phenomenon called polar absorption cap events, and that can cause communication issues. So for the communication with satellites and issues like that. Okay, it's for a limited time period, but still it's a very important issue. The other phenomena I discussed today is the geomagnetic storms induced by the coronal mass ejections. Therefore, very large events, you will have currents induced in the upper layers of the ionosphere. They themselves will induce currents lower down. And what they do is then on the ground, they find material like pipelines where the currents then can also be induced. And these currents, for example, the pipelines can cause erosion effects. What the people do, the pipeline people, they actually do, they mitigate against this effect. So it's quite well understood what happens and how to protect yourself. With the power grids, it's the same actually phenomenon. You have induced currents. They can travel and end up, like for example, big transformers can get saturated, burn out. And some of you may have heard about the Quebec event, which was here some decades ago. And it was actually what happened. They didn't have power for quite many hours because of this. And to change a transformer is not something you can do in an hour, because if there are many transformers that burn out at the same time, then you'll have to go and find them and buy them, and yeah, it's very expensive. So the grid systems, also the grid companies, they're very power companies, they're very interested in this, and also take precautions. So that's why they're interested in alert systems, because then they can shut down some of it so that the load is not so high, and in that way they can protect their transformers and power grids. So thank you. If there's any other, yeah.
Thank you. And Julia forgot to mention that was from Rachel Berkovich from Physics Today.
And thank you very much. Thank you.
Are there any other questions? Okay, if there are no more questions, then that leaves us some time to go and check Manuel's videos at the computer. And the next press conference is on habitable worlds in the solar system, and we'll actually have a speaker from the ESA's JUICE. Oh, sorry, there seems to be another question.
It's for Mr. Grant. If there's time, what was actually measured from the 2009 spacecraft to show coronal mass ejection hitting Venus? Can this be done elsewhere on any spacecraft?
The reason you could certainly do it at Mercury, if you. What you want is to be able to look from the side at the coronal mass ejection hitting the planet. In fact, the interplanetary scintillation technique only works out to about where the Earth is, so you can't do it for the outer planets. So Venus is a convenient place to do that test. Mercury, you could do it very well also. As we've seen, you can actually make predictions and find out that they're true at Mars also, but you couldn't do that with the interplanetary scintillation technique. That was done with a different technique.
Okay, this time I'm going to give a bit more time for Rachel to type. Are there any other questions? No? Okay. As I was saying before, the next press conference is at 10. It's on habitable worlds in the solar system. And we are going to have the science leader of the ESA's JUICE mission, which was, I believe, the mission you were referring to. Yes, so it promises to be interesting. Thank you all very much for coming. Thank you all to the speakers for the great presentations. Thank you.